Okay, everyone, so we are back. We are in our last lecture, and I'm going to talk a little bit about the theory of Euclidean domains, principal ideal domains, that kind of fun stuff, which is really the heart of, one of the main cool things in ring theory. So we're going to talk about it. We're going to talk about it a little bit before we sort of depart for the semester. So last time we defined a Euclidean domain. It was a ring that had one of these Euclidean functions, and I'll pull the definition here. So it was a function which was a kind of degree or norm or something like this. It had this multiplicative property, and it had this factorization, and we showed that the integers had this months ago, and then I quickly sketched out a proof that a polynomial ring had it. It's kind of a nice little argument. I left some details to you, but I think very doable ones. Let me note that there's many other important examples. So let me start today by just quickly noting that the Gaussian integers, so z adjoin I, is an example of a Euclidean domain. Okay, so what is this z adjoin I? It's the ring that's the set of numbers of the form a plus bi such that a, b is in z. Right, so it's like a lattice in the complex numbers, but it's closed. If you think about how it's defined, it's closed under multiplication. And the degree is the norm of z squared, the usual the usual norm, the complex number norm. So it's a plus bi times a minus bi, i.e. a squared plus b squared, as it's also known more commonly. Right, so just the norm, just in the sense of real numbers or irrational numbers, and you can check pretty easily that that's a degree. There's a little argument there that, again, like the polynomial ring, I won't give all the details. I'll let you ponder it, the last day or two here. But suffice to say, it's not hard to see that that satisfies the same thing. Okay, so. So there's a kind of a lot of really neat properties in Euclidean domains. So I'm gonna, again, just following Goodman, I'm just gonna kind of sketch out what happens. And the reason is that we actually did all of the gory details for the integers, and the proofs are not that different, right? So this is maybe cheating a little, but I swear it's not cheating that much. If you go back and look at what we did for the integers, you'll find that the existence of this function d was basically all we used in showing that all this good stuff works. So the greatest common divisors and least common multiples and every ideal being principal and all this good stuff. So I'll give a few sample results here in this last lecture. So for instance, let's give a sample result of that is very typical for this theory and that is very useful. So let's prove a lemma that's completely the same as what we did for integers, and you'll see how it goes almost right away. So let R a Euclidean domain, I and R an ideal, then I is principal. So then I is the ideal generated by F for some F in I. So there's just an element of I that generates the ideal. And when I say this, I mean that it's... Right, so what is this parenthesis F? It's the ideal that can be described as stuff, all the stuff in R times F. Right, so that's clearly an ideal in the ring. And now I'm saying that, in fact, every ideal is of that form. Those are called principal ideals. We won't really need this terminology, but it's worth saying. Okay, so how do you prove a lemma like that? So you think back to the proof for integers. We actually proved this for integers. We actually proved that every subgroup of the integers is the subgroup generated by one element. So that's too strong to hold in a general Euclidean domain. If you think about polynomial rings or something, there's no way that can hold. But this slightly weaker statement does hold. So you do need it to be, in the integers, a subgroup and an ideal are the same thing. That's very unusual. In most rings, that's not true, and so you need some slightly stronger assumptions. But if you have an ideal, then that is true, that they're all principal. Okay, so how do we prove this? Theorem? Well, the point is we do it the same way we did for integers, namely we look at the element of least degree in the ideal. So let f be the element, f be an element of I of least degree, right? So assuming I is not 0. So if I not equals 0, d from I to n, right? So what do I mean? I just wrote this quickly. What do I mean? If I is the 0 ideal, then of course it's principal. It's just the ideal generated by 0. So that's stupid. What if I is not 0? Then you have a function from I guess properly speaking, I should say I minus 0 to n. So since the natural numbers, okay, if I have any set of natural numbers, I can take its minimum. It's a basic fact of natural numbers that any subset has a minimal element. And so if I look, so I should say again, this was me being slightly lazy, sorry, element of I minus 0, right? So if again, the ideal is 0, there's nothing to prove. If the ideal is not 0, then you can look at the collection of degrees. There's a bunch of natural numbers, and now I can take the natural number in that collection, which is least. Right? So this makes sense. I can take an element of this ideal of least degree. And then the point is, if G is in I can write G equals QF plus R, where the degree of R is less than the degree of F. Okay? So that's just long division, the exact long division that we proved last time. Well, we didn't prove it. We said that any Euclidean domain has it, but of course, for integers or for polynomial rings or these other things, we basically proved that they have this property, right? And so the point is, okay, great, you have this, but now G is in I and F is in I. Okay, but G in I, F in I implies R, which is in fact, of course, G minus QF, is also in I, right? But the degree of R was less than the degree of F, which is an element of I of least degree. So the only way this can work out is if, in fact, R is 0. So these things together imply that R must be equal 0. So this implies that G equals QF. And that was the claim, that any element is in the ideal is a multiple of F. Right? So this, if you think about it for a minute, it's exactly the same proof that we gave for the integers. It just restocked for Euclidean domain. So now I can make a definition. Let FG in R, GCD of FG is a generator of the ideal RF plus RG, right? In other words, RF plus RG, the set of all things of the form R times F, something times F plus something times G, that's certainly an ideal in the ring, and this is in fact R times D by the lemma. And so a GCD is just any element that generates it. These GCDs are not unique. They're unique up to multiplication by a unit. But okay, whatever. I mean, this is like in the integers saying that you could switch plus and minus 1. That's true, but that's kind of irrelevant to most considerations in life, right? So a GCD of F and G is exactly a generator of this ideal. So any pair of elements have a GCD. To be relatively prime, your GCD is 1 or a unit. That's if and only if F and G generate the whole ring, right? The ideal generated by F and G is the whole ring, right? That's clear. And then from there, you can just run through your proofs for the integers and get all the same consequences. So let me make a definition. So two definitions. One, so F is irreducible if it doesn't have any factors. So in other words, so F is irreducible, F and R is irreducible if whenever F is AB, either A is a unit or B is a unit in the ring, right? So this is kind of like saying either A is 1 or B is 1, except of course now I have lots of units in the ring that might not be 1, right? So for instance, in a polynomial ring, Fx, every element of f times 1, is a unit, right? They're invertible elements. And so, of course, I can always multiply anything by a unit times its inverse, and it doesn't make any difference. So you kind of have to take these things up to multiplication by a unit. In the integers, you could get away with more because the only units are plus or minus 1. So it was like the easiest possible situation. Now it's slightly more complicated because there can be more units, but it's still very similar. Okay, anyway. And then 2, f is prime, if the ideal f is a prime ideal, i.e., what does it mean for the ideal f to be a prime ideal? It means that f divides ab implies either f divides a or f divides b, or both, right? And then the lemma is that f is irreducible if and only if it's prime. So let me just write that, f irreducible if and only if f is prime, right? And the proof is you literally just copy the proof for integers. Okay, so so I won't recall the details. I'll just say if you flip back to the section, either your notes or the section in the book on basic integer arithmetic, you will see that the only thing that this needs are basic facts about GCDs and factorization, and that's exactly what we have in this setting. Okay, let me state another lemma, which again I won't prove and just refer you to the proof for integers because it's exactly the same. Any element has a factorization into irreducibles. Let f in R. There exists irreducibles equals primes. Irreducible elements f1, fr, such that f equals f1 times fr. And this factorization is unique up to units. And if f equals g1, gl is another such factorization, then L is R and Fi equals Ui times Gi, where Ui is a unit. Okay, and again, it's like saying that if I have a product of two numbers, I can multiply them both by -1 and it doesn't affect the total answer, right? So I can do something stupid like, right, if these are irreducible polynomials, multiply one of them by 10 and the other one by another one by 1/10 and say, oh, you got a different factorization. So of course, it's not really different. It's the same up to just multiplication by stupid units. But we need to include that in the statement, otherwise it would be trivially false. Okay, so, and again, the proof of this is, long division in by exactly the same method. Once you have the function d, you have the division algorithm, then you get this automatically in exactly the same way we got it for integers. Okay, so again, I'm not going to go through the details of these things because just like with the GCDs and the ideals, it's exactly the same as it was for the integers. Just no different mathematical content. The proofs are set up. The modern proofs of these things are set up to work the same way in all these contexts. That's what's so nice about them. Okay. So Euclidean domains have these two very cool properties that we kind of see. So I'll give these definitions. Just it's the last lecture, so we won't do too much with all this stuff, but just for context. So so let R be a domain. So so R is a PID, principal ideal domain, if every ideal is principal. Every ideal I in R satisfies I is the ideal generated by some element F. So it's a principal ideal. It's generated by one element. And 2, R is a UFD, unique factorization domain, if R has unique factorization into irreducibles. Has. So unique up to units, as I stated above. Factorization, so i.e. F equals F1 FR, Fi irreducible, for all F and R. And it's unique up to units in exactly the same way I stated above there. All right, so these are two very important and interesting notions in ring theory. Euclidean domains are both. So Euclidean domains are both PIDs and UFDs. In fact, every PID is a UFD, which I guess I might prove. There are PIDs that are not. I mean, so the facts are Euclidean implies PID implies UFD. All right, so I'm going to try to prove at least some of these facts. So we've proved today that Euclidean implies PID and Euclidean implies UFD. We haven't proved PID implies UFD. The upshot is that none of the reverse implications hold. There are counterexamples in every direction. They give some good examples of unique factorization domains that are not principal. The best examples of those are polynomial rings in more than one variable. So they say ZX, which is actually a nice example. But let me give a different example. So in fact, so let me say this is fact 1. Fact 2, if R is a UFD, R join X is also. We probably won't get a chance to prove this, but that's an important and cool fact from basic ring theory. But that fact is not true for either of these other notions, PID or Euclidean. So for example, if we take f, x, y, the polynomial ring in 2 variables, right? So in other words, what do I mean by that? I mean, you take polynomials in one variable, and then over that you take polynomials in another variable. Perfectly reasonable thing to do, right? So that polynomial ring is a UFD, right? Because f of x is Euclidean and therefore a UFD. And so when we took another polynomial variable over that, that should also be a UFD, according to this fact 2 here, which, as I said, we're in the last lecture here. I probably won't get a chance to prove that. That's fine. X, the ideal generated by x and y is not principal. Okay, it's easy to check that you can't find a single polynomial in 2 variables which divides both x and y. It's kind of obvious, right? I mean, if you think about real valued polynomials, real valued functions in 2 variables, there's not one polynomial that divides into both the x projection function and the y projection function. So I think you can convince yourself of that pretty easily. So this is a non-principal ideal, but the ring does admit polynomials in several variables do admit factorizations. Okay, so those are just generally good things to know. So what I want to do in the last 10-15 minutes here is I do want to try to explain, I think, why a PID is a UFD. Yeah, this is an interesting question. Should I try to prove that a polynomial ring is a UFD, polynomials in several variable, or should I try to prove that that every PID is a UFD? Yeah, maybe I'll try to prove. I think I'll try to prove that a PID is a UFD, and I'll leave this last section 6.6 for future investigations for you guys. So that's something that I won't count. That's something that I won't count on in the exam or in this class. Yeah. Okay. So I officially declare that the very last topic of the course is factorization in principal ideal domains, and so I'll try to give a sketch of the proof that every PID is a UFD. So, all right. So that's going to be our last thing here, the last five minutes or so. I just want to try to sketch this out. So every PID is a UFD. It's a fundamental fact of ring theory. I could have gone for factorization in polynomial rings, but I'll leave that. I'll leave that for a future. Like I said, you guys can learn that in future courses if you take more advanced algebra courses. At some point in your life, you'll take, if you're on the algebra track in life, you'll take a first-year grad algebra course or something, and then you'll prove the crap out of all these things, as the saying goes. So I'll skip that, and I'll try to sketch out why every PID is a UFD. Okay. So there's the point is, why can you? So how do you show that a ring has unique factorization? So it's kind of an interesting thing. How do you prove a thing like that? So the point is, you want to try to take an element and keep dividing it by other elements, and you want to show that this can't go on indefinitely, right? So let R a PID and let F in R. So suppose, so F is F1 times F tilde. And, right, because I want to show that I have unique factorization into irreducibles, where neither are units, right? Where both F1 and F tilde are not units. I don't know why I called one of them F1 and the other one F tilde. That was stupid. I should call them F1 times F2 to keep the parity here. Okay, where both F1 and F2 are not units. Okay, then you can look at these and you can ask, can they be factored or not? And if one of them can be factored, then you can keep going. So if both F1 and F2 are irreducible, right, if they can't be factored further, done. Else, what do we have? We have F is F1, F2 is F11 times F12 times F21 times F22, right? If either or both of these can be factored further, then you split them up. So if all irreducible, done. Else, F equals F111, F112, F121, F122. This is the last one. These I'll do. F211, F212, F221, F222. Okay, you guys get the picture, right? So the point is, if any of these can be factored, you just factor them. So you can keep going. So either this process terminates at some finite level, or it continues forever, right? So what does it mean if it were to continue forever? Well, since we factored F into F1 times F2, that means that the ideal generated by F is contained in, it contains the ideal generated by both F1 and F2, right? So, so if I'm in the ideal generated by F, then I'm also in the ideal generated by F1 and F2. Okay, so in this situation, RF is contained in RF1 and RF2, incidentally, and RF1 is contained in RF11 and is also contained in RF12, and RF2 is contained in RF21 and is contained in RF22, etc. So, right, each time I factor, this ideal is contained in both of those other two ideals, right? Because what is this ideal? It's F times something, and if I'm F times something, then I'm necessarily also F1 times something, right? So what do I get? I get an if F has no factorization, right? If it's not true that there's a factorization, if this sequence continues, you get an infinite chain RF, RF1, RF1, 2. You get an infinite chain of ideals, and each one is contained properly in the next. So this is the point, right? So you get an infinite chain of ideals, and they're not equal, because if at any point they were equal, then, right, what does it mean for the two ideals to be equal? It means one of those elements is a unit times the other. But the point of this is that every time we split up into two different a multiple of two things, neither of which were units, right? So you get, so if there's no unique factorization, if there's no factorization, you get an infinite chain of ideals like this. Okay, but now the claim is that there is no such chain. The claim is that if you have an infinite chain like this, can't exist in a PID. So claim there is no such chain. Okay, and then what's the proof? So the proof is, if I have a sequence of ideals, if I naught is contained in I1 is contained in I2 is a collection of ideals in a ring,
Wow. That's so cool.
then the union of those I sub I is an ideal. Okay, and by way of proof, I'll just say that you add two elements in here. What do you get? Another element in one of these things. You multiply R by anything in one of these, you get an element of one of these. So if you think about it for a minute, you'll see that this is also an ideal. So in our case, because it's a PID, that ideal has to be generated by a single element, right? So, all right, so RF1 contained in RF, so RF contained in RF1 contained in RF12 is actually equal to R times A for some A. The union. When I say the chain is equal to it, I mean, and the union of RF1I is equal to R times A. Right? So in fact, all of these RF1I are contained in RA for a single A. Right? So what does that mean? So that means that if I take any of these elements, they are necessarily all equal to A times something. So there exists some A which divides every single thing in this chain, right? So in other words, all of these elements are necessarily divisible by this one single element A. But that's a problem, right? Because if I have this A and it's contained in the union, it has to be in one of them, right? So the union of RFI is RA. So A is in RF1I for some I. It should be 1, 1, 1, 1, 1, 1, 1 I, but I'm just indexing them by I now. So I really should have probably just called it RFI, but okay. I hope the meaning is clear. So A is in RFI because A is an element in this ideal, and this ideal is a union of these things. So A is in one of these elements. So A divides F1I, and F1I divides A. So that implies that A is, well, up to a unit. So in fact, right, A is in RFI, so F is in RF1I, so F1I divides A, and also all of these things are contained in RA, right? So A divides all of these FIs. So in particular, so in fact, RA equals RF1I, R times F1I. They divide each other, so they generate the same ideal, and so this implies that RF1I is the union overall, let's call it J, RF1J. Yeah, let's make sure to call this union J, so as not to confuse the union with this particular I picked, right? So this union is equal to that one, but then all of the rest of them are actually equal to this one, right? These guys are supposed to divide this one, they're supposed to divide into it without being equal to it, but if they generate the same ideal, then they're equal up to a unit. So, to put it bluntly, that's a contradiction from the way we constructed this thing. Okay, so that was a little bit long-winded, but that shows that you can't make an infinite chain of ideals like this in a PID, and that means that in fact you do have factorization. Okay, so every element in a PID can be factored into irreducibles. All right, so finally, so they give a nice version of this proof in the book too. So that's kind of a nice fact. And so then finally you want to deal with the uniqueness of this factorization. Suffice to say, so I won't go through the details of this, but suffice to say that you can show in a PID that prime and irreducible are the same thing. I'll leave you guys to read that proof in the book, but it has to do with most of it is just general ring theory, but the case where every ideal is principal, you get some extra property with that prime and maximal ideals are basically the same thing, almost. And so you can then run the argument that we're used to in the integers to prove that factorizations are unique. So let me just say that in a PID, in a PID, prime and irreducible, I won't write it, I'll just say it. In a PID, prime and irreducible are the same thing, and so we can again use our same kind of argument that we've been using in integers and in all Euclidean domains to show that unique factorization holds. Okay, that was a tad sketchy, but it's quite well written in the book, and so I'll just refer you to that to finish off the details. Okay, so that's the end. We really did get through almost one chapter of ring theory by the skin of our teeth here. And I will be back shortly after this video is posted to talk about some information for the final. Actually, I'll post that tonight for sure, as well as the videos. So you guys will see all this stuff today. Thank you for your patience. I know this one came out a little later than it was supposed to. It was really supposed to be out yesterday, but it will be out today, Thursday, and the information about the final will as well. So please don't hesitate to contact me if you have any issues. Thanks again for all your patience and for making this a good class despite all the crazy circumstances. So I look forward to hearing from you, and as I told you before, the final will be, you'll have the whole week to do it. I don't anticipate it being super hard or anything. I want you all to get A's, and I think you will. So please don't hesitate to contact me if you have any questions. All right, talk to you soon.